Let V be a vector space over F. V1, V2 up to Vn be vectors in V, and A1, A2 up to An be scalars in F. The vector A1V1 plus A2V2 plus AnVn, which is a vector in V, is called a linear combination of V1, V2 up to Vn. The linear span of V1, V2 up to Vn, denoted by span bracket V1, V2 up to Vn, is defined as the set of linear combinations of V1, V2 up to Vn. In other words, span of V1, V2 up to Vn equals the set of A1V1 plus A2V2 plus up to AnVn, where A1, A2 up to An are in F. Let's see a proposition. For any vectors V1, V2 up to Vn in V, the span of V1, V2 up to Vn is a vector subspace of V. To prove this, again we check that T1, T2, and T3 hold. Let S be the span of V1, V2 up to Vn. Since the zero vector equals 0 times V1 plus 0 times V2 plus up to 0 times Vn, which is a vector in S, T1 holds. Suppose x and y are in S. Then there exist lambda I and mu j in F such that x equals lambda 1 V1 plus lambda 2 V2 up to lambda n Vn, and y equals mu 1 V1 plus mu 2 V2 plus up to mu n Vn. Then x plus y equals bracket lambda 1 plus mu 1 times V1 plus bracket lambda 2 plus mu 2 times V2 plus up to bracket lambda n plus mu n times Vn, which is a vector in S, so T2 holds. Now for mu in F, mu times x equals bracket mu times lambda 1 times V1 plus mu times lambda 2 times V2 plus up to mu times lambda n times Vn, which is a vector in S, so T3 holds. Let B and Vi be vectors in Rm. When is B in the span of V1, V2 up to Vn? Consider the m by n matrix A, which consists of V1 up to Vn as its columns. B is a vector in the span of V1, V2 up to Vn, if and only if there exist x1, x2 up to xn in F, such that B equals x1 times V1 plus x2 times V2 plus up to xn times Vn. This happens if and only if B equals A times x, for some vector x in Fn. Let's see an example. Let V1 be the vector 1, 2, 3, V2 be the vector -1, 0, 1, and V3 be the vector 3, 1, -1. What is the span of V1, V2, and V3? Let B be the vector B1, B2, B3, and A be the matrix 1, -1, 3, 2, 0, 1, 3, 1, -1. Then B is in the span of V1, V2 up to V3, if and only if A times x equals B has a solution. So we solve this system, namely 1, -1, 3, B1, 2, 0, 1, B2, 3, 1, -1, B3. Using elementary row operations, we subtract 2 times the first row from the second row, and subtract 3 times the first row from the third row. We have 1, -1, 3, B1, 0, 2, 5, B2 minus 2, B1, 0, 4, -10, B3 minus 3, B1. Now we subtract 2 times the second row from the third row, and get 1, -1, 3, B1, 0, 2, 5, B2 minus 2, B1, 0, 0, 0, B3 minus 3, B1 minus 2 times B2 minus 2, B1. Now the last entry is B1 minus 2, B2 plus B3. If this entry is non-zero, then the system has no solution. If this entry is 0, that means that we have a 0 row, so the system has infinitely many solutions. Hence, B is in the span of V1, V2 up to V3, if and only if B1 minus 2B2 plus B3 equals 0. That is, the span of V1, V2, and V3 is a plane in R3 defined by the equation B1 minus 2B2 plus B3 equals 0. Suppose now V1, V2 remain unchanged, but V3 equals 3, 1, 0. Then we solve the system 1, -1, 3, b1, 2, 0, 1, b2, 3, 1, 0, b3. Using the same elementary row operations as before, we get to the system 1, -1, 3, b1, 0, 2, -5, b2 minus 2b1, 0, 0, 1, b1 minus 2b2 plus b3. The system has a unique solution for any given b1, b2, and b3. So b is in the span of v1, v2, and v3 for any given b, which means that the span of v1, v2, and v3 equals the whole of R3. Then, for any given b, there is a unique way to represent b as a linear combination of v1, v2, and v3. Let W be a vector subspace of V. If W is the span of v1, v2 up to vn, then v1, v2 up to vn is called a spanning set for W, and we say that v1, v2 up to vn span W. For example, the vectors e1, e2 up to en, where each ei has 1 in the ith position and 0 elsewhere, they span Rn. Indeed, for any x in Rn, x equals x1 times e1 plus x2 times e2 up to xn times en. Consider the three vectors v1, v2, and v3 from a previous example. v3 is a linear combination of v1 and v2, because v3, which is the vector 3, 1, -1, equals 1/2 times the vector 1, 2, 3 minus 5/2 times the vector -1, 0, 1, which equals 1/2 times v1 minus 5/2 times v2. Then lambda1 v1 plus lambda2 v2 plus lambda3 v3 equals bracket lambda1 plus 1/2 times lambda3 times v1 plus bracket lambda2 minus 5/2 lambda3 times v2. In other words, the span of v1, v2, and v3 equals the span of v1 and v2, so v3 is redundant. Now let's define linear independence. v1, v2 up to vn in V are called linearly independent if lambda1 times v1 plus lambda2 times v2 plus up to lambda(n) times vn equals 0, implies that lambda1, lambda2 up to lambda(n) are all 0. In other words, there does not exist lambda1, lambda2 up to lambda(n) in F which are not all 0, such that lambda1 times v1 plus lambda2 times v2 plus up to lambda(n) times vn equals 0. In other words, there is no linear combination of v1, v2 up to vn which gives the 0 vector, except the case when all scalars are equal to 0. On the other hand, v1, v2 up to vn are called linearly dependent if they are not linearly independent. In other words, there exist lambda1, lambda2 up to lambda(n) in F which are not all 0, such that lambda1 times v1 plus lambda2 times v2 plus up to lambda(n) times vn equals the 0 vector. In other words, there is a linear combination of v1, v2 up to vn which gives the 0 vector, and not all scalars are equal to 0. Let's see some examples. When there is only one vector, say v1, it is linearly independent if and only if v1 is not the 0 vector. Indeed, as long as v1 is not the 0 vector, then no matter what scalar you multiply to v1, it will never be the 0 vector. When there are two vectors, say v1 and v2, they are linearly dependent if and only if lambda1 v1 plus lambda2 v2 equals the 0 vector, where lambda1 and lambda2 are not both 0. Say lambda1 is not 0, then v1 equals negative lambda2 over lambda1 times v2. In other words, v1 and v2 are scalar multiples of each other. So, v1 and v2 are linearly independent if and only if they are not scalar multiples of each other. As a third example, v1, v2 up to vn are linearly dependent if any one of the vectors is the 0 vector. Indeed, say v1 is the 0 vector, then for any lambda1 which is non-zero, we have lambda1 times v1 plus 0 times v2 plus up to 0 times vn equals the 0 vector. Note that if v1, v2 up to vn are linearly dependent, then at least one vector can be expressed as a linear combination of the others. Indeed, assume λ1 is non-zero, then v1 equals negative 1 over λ1 times bracket λ2 times v2 plus up to λn times vn. In this case, the span of v1, v2 up to vn equals the span of v2 up to vn. Second, let V be f to the m and A be the matrix v1, v2 up to vn, which has size m by n. Then v1, v2 up to vn are linearly independent if and only if A times x equals the zero vector implies that x equals the zero vector. This is just the definition of linear independence by rewriting the linear combination of v1, v2 up to vn as a matrix times a vector. These vectors are linearly dependent if and only if the equation A times x equals 0 has non-trivial solutions. Let's prove a proposition. Any subset of a set of linearly independent vectors is linearly independent. To prove, suppose v1, v2 up to vn are linearly independent. By reordering the vectors if necessary, we may assume that the subset is S, which equals v1, v2 up to vk, where k is less than n. Assume for a contradiction that S is linearly dependent. Then there exists λ1, λ2 up to λk in F, not all zero, such that λ1 times v1 plus λ2 times v2 plus up to λk times vk equals the zero vector. Now, λ1 times v1 plus λ2 times v2 plus up to λk times vk plus 0 times vk plus 1 plus up to 0 times vn equals the zero vector. We label this as star. Since at least one of λ1, λ2 up to λk is non-zero, star means that v1, v2 up to vn are linearly dependent, which is a contradiction, and this completes the proof.